This is a rather interesting unit. It was sent to me to do a sort of autopsy on as to why it had failed, because it was blowing fuses all the time. It's a V-Phase VX1 energy saving device, and it basically goes in at your distribution board and it lowers the voltage to your house. And it's, it starts off being quite simple. It starts off being a nice simple buck transformer idea, but not heavily rated buck transformer, and then gets a lot of circuitry. The thing I just took off was a heatsink, and it had 4 IGBTs attached to it. Now, if I take a look at those IGBTs, an IGBT is a power transistor, and it's a combination, it's a hybrid. It's like the traditional bipolar transistor, the chunky NPN, PNP type one, but because of these applications, they require a lot of really high current driving for the traditional bipolar transistor. So what they do, with IGBTs, insulated gate bipolar transistor, they combine a MOSFET in. So you end up with the sensitivity of a MOSFET, which is very easy to turn on, and you end up with the ruggedness of a standard bipolar transistor. It's a good compromise. They're commonly used in industrial traction type applications. But these particular ones are all showing a dead short across their collector and emitter, suggesting that they've had an absolutely horrific experience. They're dead. They're also showing leakage to the gate on some of them, not all of them, which is suggests quite dramatic failure inside it. There shouldn't really be any coupling to the gate. But interesting. But they're all seemingly dead. And that may be part of the reason. It was blowing this fuse apparently, and the fuse is actually an FF type fuse, which is a very fast semiconductor rated fuse, and I'm wondering if that's actually in line with the primary of the toroidal transformer. I'm not sure, because ultimately toroidal transformers are a horrific load to switch. But anyway, let's look at the theory of this and then look at how I can try and work out how this works and what these IGBTs were for. So we'll go into the theory of a buck transformer first. So we'll base this on the toroidal transformer, which is that donut shaped transformer, because it's a nice simple arrangement. So here's a transformer. And a buck transformer is used to either buck or boost the voltage of a mains supply. So supposing we've got a main supply come in, and we'll just use nice round figures, we'll say 100 volts. So 100 volts, and we've got 100 turns round the primary of the transformer, 100 volts, 100 turns, which is 1 volt per turn. And this is the mains in. But we want to drive a load which we want to drive it at 90 volts instead of the full mains 100 volts. Now, if you wanted to do that with a full-blown transformer, and you had a traditional transformer with an isolated primary and secondary, and you put the 100 volts in, and you got your 90 volts out, then if it was something like, let's say the load's 10 amps, that's quite a lot. That would be 900 volt amp rating for that transformer. And that's quite a big transformer. It would be a really heavy transformer to actually achieve that. It would be the best part of a 1 kVA transformer, which you'd probably have to use to allow for the losses. But if you use a buck transformer, it only has to be rated 100 volt amp, because all it's seeing is the difference in voltage. So if you then wind on a secondary winding, which is only 10 turns, and so that's 10 turns, and it's seeing 1 volt a turn, so that's 10 volts. And if you take the main supply to the load, so let's put the load here, and we're wanting 90 volts at the 10 amps. We take one connection from the main supply, goes straight to that. The other connection from the main supply, because this is I'll write mains in. The other connection doesn't go to the load. If it went to the load would be seeing 100 volts. Instead, it goes via this winding. And then it goes to the load. And that winding is effectively in series of the load. And depending on the polarity that you put that winding, it will either increase the voltage by 10 volts to 110 volts, or it will drop it by 10 volts to 90 volts from this original 100 volts. And obviously this can apply to 120 volts, it can apply to 240 volts, even industrial supplies, 600 volt supplies, you could apply the same technology as long as it's AC, because the transformers require AC to couple through. And because this coil, the secondary coil here, is only seeing the 10 amps at the 10 volts, the transformer only needs to be rated 100 VA, 100 watts, 100 volt amps. So that's the principle of a buck or boost transformer. And that's pretty much what they've done here in a way, except this is designed to lower the main supply from 230 volts apparently to 220 volts. And it's quite an invasive unit. It's not subtle. It's not. They present it as a simple task that they can get their guy to come out. It'll just stick it into your consumer unit, and that'll be it. It requires a significant modification to your consumer unit. I'll show you a consumer unit. In fact, consumer unit is the name for a home distribution board in the UK. So here is a typical split load consumer unit, made of plastic for maximum combustibility. It's got the main incoming breaker, which is just an ordinary switch breaker. It's not a breaker, it's just an isolator. I shouldn't refer to that as a breaker because it's not a breaker, it is an isolator, that's its correct name. And the power comes into that, live and neutral, and then it comes out the bottom of it, and then feeds into a separate breaker, earth leakage breaker, an RCD, residual current device, or ground fault interrupter as it's known in some parts of the world, for each section of breakers. So it goes into the breaker, and then each one has the neutral coming out, going to its own separate neutral bars, because you can't use one common neutral bar. Each RCD and its set of breakers has to have its own separate bar, and the neutrals can't be combined, because if they are, it will result in imbalance of the current going back through this breaker and cause false tripping. So this is a typical arrangement in the UK now, that you can mix and match breakers. You can say, I'll have lighting and power downstairs and lighting and power upstairs. And it means that if you have an earth leakage problem in your house, it's not going to just kill power to the whole house, which was what used to happen, and what certainly happens to this house when there's a fault, because this house is still protected by one main RCD. And that's partly because the electrical utility company supplies that, purely because they want the power. If they have an outage in the local neighbourhood, they want the power to my house to go off completely, so that ultimately, when they close the power in at local small substations, the load is picked up slowly as people reset their breakers. I think that's ultimately why I think they do it. It's also a good safety feature, as common with rural electrical supplies. But anyway, to actually put this unit in, the big chunky unit, you actually have to put in an extra breaker, a 50 amp breaker, to feed that unit. And then that has to come back and feed a set of circuit breakers dedicated. So there are some significant modifications required. In the case of this, that would move down, you'd have another link coming out, going through the 50 amp breaker, and then it would be coming back and it would feeding, say, this bank of breakers. It wouldn't feed the whole house because it's not rated to feed heavy heating loads like showers, which is going to be one of the highest loads in a house, or electric heating, or things like water heating. They say it's really just for things like lighting and ring main circuits and circuits in your kitchen. And that's a bit odd because, if I move this out the way now, this thing is actually rated for a continuous load of just 8 amps, which isn't a lot. Even with our 240 volt supply, that's not a lot. That's 2 kilowatts. And it's got a peak rating, a short duty cycle rating in bursts of 20 amps. And if the transformer starts getting too hot, if the load's really high, it will bypass the transformer, and it's got a current sensing coil here that feeds this excessively complicated circuitry. And this thing here is an 80 amp bypass relay. Yes, that thing with the ominous word China printed on it is a tiny little relay with the big terminals coming out the bottom that I think they're spot welded onto the copper bus bars here. And they are, that will theoretically bypass this, but obviously it can't bypass it while it's on, because if it did that, it would be shunting out the secondary winding, which is this big coil here. And I'm guessing it can't turn the power to the transformer off and then bypass. Maybe it can. I'm not 100% sure if it can. What would happen if you turned the primary off? I guess it would just act like a choke in series with the circuits briefly. And I don't know if the IGBTs are to try and drive the primary in some sophisticated manner that to avoid, when this cuts in, to avoid the lights suddenly changing, you know, when this is bypassed, to avoid the lights suddenly snapping to a different intensity, then I wonder if this does a soft, gentle ramp down of the primary before the bypass kicks in. I'm not 100% sure. Or if it's doing anything more sophisticated. It's certainly got a lot of circuitry. It's quite hard to trace out because the circuit board is not just double layer, it's multi-layer. There's layers going on inside the circuit board, and it's obscuring. It's making it hard to actually see through the circuit board and even trace a lot of the tracks on the top or the bottom. But there are various other safety features built in here. You've got this connector for the transformer has 6 connections. It's got the primary connection for the primary winding in this big toroidal transformer. It's got a thermistor to detect the temperature of the transformer, and it's also got a couple of wires going up that read as a dead short, which I'm thinking might be a last resort thermal fuse if it gets too hot. It's a lot of protection. And then of course there's this fuse, 25 amp fuse in line to limit, you know, short circuit current through the transformer, and then there's a big, huge, high current thermal cutout sitting on top with a thermal coupling onto the transformer itself, which will also cut out if a fault occurs and it starts overheating. So lots and lots of circuitry. And I've got mixed thoughts about whether this is actually, I certainly wouldn't want one of these put into my house at all because it's quite invasive. It does involve those significant modifications to the consumer unit, and they say easy to put in, easy to take out, you know, for qualified electricians. And well, these days, qualified electrician can be a 2-day course, which, you know, I'd hate to think that, you know, you'd end up with a Part P. Kitchen fitters coming and installing something like this using maybe the 2.5mm twin and earth they had left over after they broke a ring main circuit somewhere. Yes, that's me having another snipe at the kitchen fitters. But yes, I'm not convinced about this for various reasons, particularly because modern houses have a lot of electronic loads in them. Now, one of the features they say, by reducing the power to tungsten lamps, it saves a lot of power, and you know, things like your washing machine will use less power, and this is all slightly bullshit, because if you consider, if this is the electricity meter and the mains coming in, so there's the mains in from the supply, so this is the meter, it has live in, it's got neutral in. Neutral is just linked across inside, but a tap is taken off for monitoring the voltage. Neutral comes back out and goes to the load. So we'll just say this is the load, via protection of course. So you get live in and live out. And then we've got this buck winding that's in line to the load to drop it, drop the voltage. Now the meter measures the amount of current going between live and neutral, and it measures the voltage it's to reference, you know, it's to meter that at, by measuring between live and live and live out, but it measures the voltage from live to neutral. So it's seeing, say for instance, let's go by that standardised voltage of say 100 volts, which is nonsensical. I don't know if there's a country in the world that has a 100 volt thing, but we'll just say here's, based on the previous sketch, I will say this is the 100 volt supply, and here's the load operated at 90 volts. Now, if this is an electronic load like a washing machine, there are a couple of things. Firstly, the heater in it. British washing machines use heaters, and they're aiming to get the water up to a specific temperature. They're aiming to get maybe up to 20, 30 degrees centigrade or whatever. And if you supply them with 90 volts instead of the 100 volts, it's just going to run for longer. It's going to use the exact same amount of energy. I mean, there's no ultimate loss, but it is going to use the same amount of energy to get that water up to the same temperature. However, the motors in them are electronically controlled, and if it sees a lower voltage, it's not interested in the voltage to a degree. All it's really interested in is getting the washing machine drum up to the correct speed, and if it sees that it's not up to the correct speed, it will increase the current. And you'll end up that the machine will effectively be drawing more current at the lower voltage to achieve the same drum speed because it's monitoring the speed of the drum itself. But that current will be consistent from the live in, right through there, through the buck and through that. So the meter's actually going to see a higher current being drawn by that machine, but it's also going to see it referenced to the 100 volts that it was measuring at the mains incoming supply, and that's how it will meter it. So that's actually going to cost more for the electronics loads, and that's also going to apply to things like LED lamps with the little switching power supplies. They're aiming to put out 3 watts regardless. Now, one place it will save a bit of power is tungsten lamps, but there's a bit of a caveat to that as well. It will save lamp life, it will certainly extend lamp life considerably, but tungsten lamps, if you reduce the voltage by 10% or whatever it is, the intensity doesn't go down by 10%. The intensity for that slight reduction in power drops to, well, if you reduce it by 5%, it goes down to about 80% intensity. It's not linear. So you're getting much less light for a small reduction in the power. So I'm not sure that's actually much of a saving. Also, if this thing's cutting in and out, because the 8 amps isn't rated, it's, you know, if it's got a few loads on the kitchen, then it's going to be cycling in and out. And I wonder if it does soft ramp, because otherwise you're going to get sudden brightness change in the lights. Other loads, the tumble dryer. The tumble dryer needs X amount of energy over X amount of time to dry the clothes. It's going to run for longer to dry the clothes. A heater with a thermostat is going to, like even a kettle, it's going to draw just as much energy. I don't see any advantage to these units at all. And this is perhaps why they're a type of product that you'd find lots of slick-suited salesmen going around old ladies' houses and pushing them on them and telling them how wonderful it was and everything would be, you know, they'd save so much money. And this company even has quite lengthy, quite boring reports, which have the backing of electrical power retail companies. I won't say power generation companies, I'll say power retail companies, marketing type companies that show how much power it's saved over X period of time, and I'm not convinced. I think they might just have picked the best results, because I don't see in a modern installation this unit actually doing anything other than using a bit of power, not saving a lot, compromising things, making things run a little bit, you know, longer than they would have normally. I'm guessing fridges would also have to run a bit longer to achieve the same temperature if the compressor is being driven at a lower voltage. So it's interesting. It's an intriguing device, but to be honest, yeah, I think this is in the category of snake oil sort of thing. They do use buck transformers successfully in specific industrial applications. I can think of factories where, in the bad old days, 240 volt supply in the UK, you'd get machines from Holland that would be rated for 220 volts, and that voltage difference would actually have an effect. It would make transformers and motors run hotter, and that's where it was useful to have buck transformers. But systems like this put in a domestic environment, I just see that as yet another way to butcher up electrical installations. So it's interesting, but yes, not very impressive, I have to say. It's not something I'd ever get involved with. Okay, a little bit of research later. It turns out that V-Phase went out of business. I'm not sure if they've got a current reincarnation, because it turns out they've gone out of business before and they've bought their own assets and relaunched. So this is obviously an ongoing thing. I'm not sure if they have a current manifestation. But it made me also think of when I was with Hussmann. Now, Hussmann Refrigeration, quite often companies went around promoting energy-saving products for industrial refrigeration plant. And you'd go into the panels and find these circuit boards with blinky lights on them and wires going to random bits in the control equipment, and the service department of Hussmann would tend to come in when they took over a contract and they'd strip all of them out. They'd bypass them all, they'd remove them, and suddenly all the equipment got more reliable. There were less call-outs because the equipment was actually being interfered with by these energy-saving devices. That, you know, compressors were stalling and burning out. You know, it was really messing things up. But anyway, at the time I suggested to Hussmann, maybe, since it's obvious it's just such a big market selling to supermarkets, these energy savers, why don't I just design a box with lots of blinky lights and absolutely does nothing at all, and it could be sold at great expense an energy saver, and it would probably save them money in the long run. So with that in mind, I've decided to redesign this. So let's get the notepad, and I notice there's a red and a green LED, and if we look at the cover of the V-Phase, it's apparent, I took a look also at the IET forums where they've obviously discussed these as well, and they've done technical analysis. Note, here's the two indicators, mode and power. Okay, right, I'm noting those two LED indicators, and the opinion was divided between people who had attended their seminars and got all pumped up and, woo, we're going to save lots of money, we're going to make a fortune selling these. £300, that's $450, plus the installation cost units, plus you might have had to change the distribution board, so quite a lot of money really. You're going to, you know, not going to pay back in a hurry. But all these guys are all pumped up. Yes, I went to the seminar and it was someone who really knew what he was talking about. And the other people that said, I've just done some tests and no, in a modern house it's not going to save a penny. Yeah, I'm with the latter. But anyway, let's redesign this. So I don't want big heavy cables or excessive. So let's, here's the unit. So with its little indicator lights and the consumer unit down below, and I'm thinking out a suitable neutral bar, I'll take a wire in, and out one of the lighting breakers, yeah, 5 amp, that's fine, we'll take a wire in as well. And the circuit diagram in here, we'll go for, well, let's say live, we'll go through a capacitor. You know what I'm doing here, don't you? 100 nanofarad capacitor. Maybe even just include that 1 mega ohm discharge resistor across it. And here's the neutral. I don't need an earth because it's a plastic case and because I'm reckless that way. So, and then we'll go through a bridge rectifier. I'm doing the really posh luxury version, by the way. So bridge rectifier. Actually, you know what? I'll include a 1K resistor here. That'll double up as a fuse, so I'll leave that line in the middle of it. And the output will be 2 LEDs. There we go. This one's going to be red, and it's going to be active. It's going to have the label active. And this one's going to be green, and it's going to show power. There we go. And that is not only going to make the unit much cheaper, I would say, I think I could let them have that for 100 quid, plus an installation charge of 50 quid. It's not going to take very long. I mean, if there was a socket nearby, you could just plug it into it. And obviously, because the red and green LED would be lit, they'd be going bing, 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 bing. Oh, look at them, they're so bright, they must be saving power. That everybody would be like showing their friends and going, oh wow, look, look. Its LEDs are lit, it must be saving power. And they'd be really happy. And you know what? I would give that a 10-year warranty with a full money back guarantee if those little lights actually ever went out. That's why I'd use basic red gallium arsenide LEDs and gallium phosphide to make sure they're nice and reliable. So that would, yeah, which is a lot better than the 5-year life expectancy of the original unit. That's not going to pay back itself at all over 5 years, is it? So yes, Big Clive's Super Energy Saver. I'd actually get a big sticker made for the front that would say like, Energy Saver! It's spelt right, probably. And then some zappy name like, well, I can't do 2000 because we passed millennium, so 3000 plus. Yeah, that should work. That should be a lot more serviceable than this thing. Since having my Energy Saver 3000 Plus installed, my utility bill has gone down so much that the utility company now pays me. Thank you, Big Clive, for making this incredible technology available to people like us.